Now we're going to look at limits in the form of a graph. So we're going to use the following graph to answer the questions. And again, this is all in your notes, so you don't have to try and copy this. So use the following graph. We see that it's not a uniform graph at all. It's not a function graph that we would normally think of. It's a piecewise because it kind of jumps all over the place. The first question is find f of 1. So I want to know the y value when x is equal to 1. So I come over to the graph. There's an open circle there, so that's not it. There's an open circle here. That's not it. So f of 1 is actually 2. That's where we have the closed-in circle at. The next one, limit as x approaches 0 of f of x. So here's 0. And I'm going to put my finger on the graph, and as I get closer and closer to 0 on either side, the value that it's going to is 2. It doesn't matter that f of 0 doesn't even exist. All I care about is I'm getting closer and closer to it, what y value is it actually going to. Next we have limit as x approaches -1 of the function. So here's -1, and we can see it goes to 1, and it actually exists there too. That's going to be a continuous point. We'll talk about that in the next section. Limit as x approaches 3 from the negative direction, or from the left. So remember that negative superscript means from the left. So I want to get closer and closer to 3 from the left. It's going towards 0. Limit as x approaches 3 from the right. So here I'm going to put my finger on the function and get closer and closer to 3. Well, that value is going towards 1. So therefore, the limit as x approaches 3, because it's different approaching from the left and the right, does not exist. F of 3. Well, that's where the closed circle is at 3. So f of 3, we get 0. Limit as x approaches -4. So I have -4s over here. Put your finger on the graph as you get closer from both the left and the right hand side. That is going to 1. And then the limit as x approaches 3.5. So I'm up here. 3.5 is right here. So that limit from the left and the right, it's just a horizontal line. So that is going to be equal to 1. Now we want to find the limits of the following piecewise function. So because it's not drawn for us, first thing I'm going to do is draw it out and see what we get. So f of x is x squared when it's less than 1. I want to start with that. So it's a parabola sitting right on the vertex, is right on the origin. It's facing up. So less than 1, I'm going to put an open circle there, and then I'm going to just draw out my parabola. All right, so this is open. Doesn't look open, but it is. And then from 1 to 2, it's equal to x. So if you plug in 1 to this, for x is 1, you get y is 1, so it does actually get filled in. And then I'm going to go up to 2, put an open circle again, because that's where it stops, but it's not included. And then lastly, 2x minus 1 when x is greater than or equal to 2. So if you plug in 2, you get 4 minus 1 is 3. So I'm going to do a jump up. And then the slope is 2. So sorry, I'm running into my graph there. So I want to look at the limit as x approaches 1. So here's 1 on my graph. If I approach it from the left or the right, it's going to the same value. So that's equal to 1. And I'm going to show you how to do it without the graph in a second. And then the limit as x approaches 2. Well, if you go from 2 on this side, it's going towards 2. And if you approach 2 on the other side, it's going towards 3. So that does not exist. So if you didn't want to graph this whole thing out, you can just look at limit as x approaches 1. Well, you plug in 1 to this one and this one as a boundary. When you plug in 1 here, you get 1 squared is 1. When you plug in here, you get 1. So without graphing it, I know that the limit has to be 1. And then for the other one, x approaches 2, well, these two pieces have a boundary of 2. So you'd plug in 2 directly into it. You get 2 there, and then 2 times 4 is 4 minus 1 is 3 there. Because these are giving you 2 different values, when you plug in 2, then you know it doesn't exist. So even without drawing it out, we can tell that that does not exist. So I'm going to quickly go through this theorem, the limits, because really you don't really use them. You just look at what you're working with. But if you have the limit as x approaches c of f of x is L and g of x is m, if you want to add them two functions together, you just get L plus m. If you're subtracting those functions, you get L minus m. If you multiply the function by something, a constant, you just get that constant times whatever the limit was. Product rule, if you have two functions multiplied together, those limits get multiplied together. If you have them divided, those limits get divided, assuming or assuring that the m term in the divisor, in the denominator, is not equal to 0, so we don't have division by 0. If you take something to a higher power, you take that limit to the higher power. And if you take the root of the function at that limit, then you're going to take the root of whatever the limit was to begin with. And again, this is a theorem, so it's good to talk about them, but when you're actually looking at problems, you're not really going to think about limit laws. You're going to take the limit of whatever that's in front of you. So I don't want you to think of this like this thing that you have to memorize, because it's more intuitive. When you're taking the limits, the first thing you always do is a direct substitution. So the first thing I'm always going to do is just plug it in and see what I get, which is why a lot of these laws you never even think about. If it doesn't work, then you have to do some other things. So what we're going to be doing is looking at indeterminate form. And I think I need to start another one so that we're consistent.